In this videotape, we're going to talk about modules and specifically module mechanisms in C and C++. And a good place to go for notes on this lecture is my lecture notes, and it's listed under modules in C and C++. So first thing we need to do is provide a definition for what is a module. And a module is a set of interrelated files. Set of interrelated files that share their implementation details but hide them from the outside world. The classic definition or example of a module are different kinds of implementations for data types. So for example, I might have a list module. And in object-oriented programming, lists typically contain a container object. So that might just be the container object itself, just might be called the list class, and then a node class. So for example, list node. And typically, these two classes want to share their implementation details. For example, knowledge about the names of the instance variables, whether they're named next, previous, whether they're singly linked, doubly linked, etc. And you have seen how in object-oriented programming a class can control access through public, protected, and private. But it turns out that that's a little doesn't provide all of the granularity that we would want, because public would mean we have to share our details with the entire world. Protected says we will share our details with our subclasses but no one else, and private says we won't even share details with our subclasses. None of those three access protections cover this case where we want to share the implementation among list and list node, but we don't want to make one a subclass or the other. I know we could make list node be a nested class of list, but let's say we don't want to do that. We really want to have a set of files sharing their implementations. Neither C nor C++ provides a great module mechanism. Java provides a much better one. In this lecture, we're just going to go over the basic module mechanisms in C and C++. So the easiest thing to do is to illustrate C's module mechanism with an example. So C provides a rudimentary information hiding using void stars. As an example, let's say I want to create a stack. And the way I can do it is I can create a stack.h file that contains a list of the functions I wish the user to see. So this is the API, and I can, as you see here, use a type def to define my type, which is stack, and to prevent the user from knowing how it's implemented, I'm just saying that the stack type is a void star, that is a pointer to a void. Now you can see that in the rest of the .h file I'm referring to the stack type, but because it's a void star, the user has no idea how it's actually being implemented. Now when I go to my stack.c file, I actually define the struct that's going to contain my object, my stack object. So in this case I call it my stack. You can see it has a size, an array for containing the data, and an integer representing top, which I know should be a semicolon there. And then I have the implementation for my various functions. So for example, you can see stack new is returning a stack, And you can see that I actually use the myStack data type for creating a stack object and for initializing the variables. But then when I return it, I cast it to a stack object so that I can hide the implementation from the user. Similarly, when I pass in a stack as a parameter like I do in the push method, the first thing I do is I unpack it, so to say, by downcasting that type to a myStack pointer. So inside the .c file, I'm entitled to know that a stack type is really a pointer to a myStack struct. However, because I defined myStack inside of the stack.c file, not inside the .h file, this declaration is considered to be local to the .c file and therefore is not viewable from the outside world. I could have, if I wanted to make it visible to the outside world, in stack.h, I could have declared it to be an extern, but I decided not to do that. So if I had wanted, well, I can't easily show it here, so I won't, but I could have declared up here extern struct myStack, and then even when I defined it down here, it would be visible up in stack.h. Okay, so that provides rudimentary data hiding. Also, you notice that I had to actually prefix the names of my functions with the name of the type, and that was to prevent name collisions with other packages that might also be implementing push pop. For example, a queue might use push and pop. So that's another limitation of C, is that everything ends up in the global namespace, and so we have to be very careful when we define new libraries to make sure that we create names that don't conflict with possible names from other libraries. Okay, so that takes care of how we can do a certain amount of information hiding in C. And you'll notice that this doesn't even really rise to the level of a module because we were only talking here about one file. So this wasn't really even so much about a module implementation as it was about information hiding. So now let's move on to C++, which has a little bit more support for modules using something called friends and namespaces. So friends provides a way for us to be able to share implementation amongst multiple classes. So I might say class list node, and then use the friend keyword to indicate that list, the class list, is my friend, and it's allowed to look at my implementation, both public, protected, and private variables. Now, friends is not a two-way street. Just because I say that list is my friend doesn't mean that I can now look inside list's implementation. List has to reciprocate by saying that list node is its friend. So you can already see one potential problem, which is that if I have n files, then in each of those n files I'll need n-1 friend declarations, giving me a total of n times n-1 friend declarations, which gets to be pretty tedious. In addition, were I to add a new file, so I add an n plus first file, okay, that means that I'm going to have to place let's call this new file A, I'm going to have to, or new class A, that means I'm going to have to declare that A is a friend of my initial n files. I probably should have said classes here. So that's n friends, and then within A, I'm going to have n declarations saying that the n existing classes are friends of mine. Hence, just to add A, I'm going to have to use 2n additional friend declarations. And as you can imagine, that can get buggy pretty quickly. However, it does allow us to share our implementation. The second kind of kludgy thing about friends is that, let's say I create a subclass of a list. Let's call it, or a subclass of list node. So let's call it doubly linked list node. Okay, and call it public implements from list node. You would think that because we're inheriting from a list node, that list should be our friend. You would be wrong. I have to also put the friend declaration here in dlist node. Okay, and similarly, if I had a class dlist and it inherited from list, okay. So going back to my previous slide, you might think that because list is a friend of list node, that surely doubly linked list would also be a friend of list node, and you would be wrong. I actually have to add as an explicit friend doubly linked list to my list of friends. So it really doesn't even extend down the subclass hierarchy, creating another issue with friends in C++. Okay, so that takes care of friends. There is a second module-related concept in C++ called namespaces. And you've probably seen them in C++, because if you say something like # include IO stream, you've probably got in the habit of saying using namespace std. And what you are doing is saying that any name defined in the IO stream is now going to be included in the current namespace. So for example, cin and cout are two names defined in IO stream, and they are now defined for us in our namespace. If I did not have using namespace, then I would have to prefix standard in and standard out with the name of the namespace to which they belong. So namespaces provide a way of partitioning up our namespace so that we don't necessarily have namespace conflicts. So, as an example, let's go back to our notes, and here's two namespace declarations in C++. So I'm creating a namespace first IBM, and you can see I'm wrapping it around the declarations for 4 classes: stack, list, list node, and consult. And then I have another namespace called Apple, and if you look closely, you'll see that the first 3 classes duplicate the ones in namespace IBM. However, because they're in separate namespaces, they don't collide with each other, and the C++ compiler is happy when we declare them. The namespace operator is used just in the .h file. So you can see here I have an example with IBM where I put namespace IBM, and inside it I have a class consult, and you see I have a method getLeft. Then in my .cpp, I include ibm.h, take care to say using namespace IBM, and now I can, I've added all my method names or class names from IBM into my current namespace, and hence I can go ahead and define things without prefixing them with IBM. If I take this out, the using, then in order to declare the method, I would have to prefix the class name with IBM : : So it's a second layer of indirection in order to get to the actual method name. And there are three ways to access members of a namespace. First of all, you can simply prefix them with the name of the namespace. Secondly, you can say import just one member into the namespace, the current namespace. So here I'm just importing the stack class from IBM into my namespace. And the third thing I can do is import everything, saying using namespace IBM. And now everything from the IBM namespace is included in my current namespace. Now this could be an issue if I import two different namespaces that have similar names or the same names. And you can see here it's okay to create a new instance of consult, because if I go up here, you'll see that consult is only in the IBM library. But if I try to create an instance of stack, that confuses the C++ compiler because it's both in Apple and in IBM. Therefore, it's going to give you a compiler error. The way to get around it in this case would be to prefix stack with the name of the namespace and a : . So that gives us a brief introduction to the module mechanisms in C and C++. Remember that with C, what you're going to be doing is using void stars to get some implementation hiding. In C++, you can use friends, which are going to allow you to share implementation among several classes, but require up to n² friend declarations to make it work. And you can put different classes into different namespaces, thus avoiding the pollution of your program's namespace. If you have two third-party vendors, there's no problem with the names colliding. And notice we managed to get rid of, with namespaces, we get rid of the problem of having to try to create unique names for our functions. In C++, we would just say that stack was part of, say, namespace stack, and now we could just put our functions into there. That concludes our discussion of module mechanisms in C and C++. In a separate videotape, we'll talk about module mechanisms in Java.